Planets are nice, but they're small, messy, and frankly, limited. In space, we could build habitats bigger than anything nature has ever created. The real question isn't whether we can build giant space habitats, it's how enormous they can actually get before the laws of physics finally say no. Why settle for a cramped space station when we could engineer worlds larger than planets themselves? For over a century, visionary scientists and science fiction engineers have dreamed of habitats that don't just keep people alive in space, but forge entirely new worlds, vast landscapes the size of towns, counties, or even entire continents. Our imaginations can conceive habitats grander and more breathtaking than anything nature has ever produced. And the burning question is whether known science actually allows us to build them. So today we're going to ask, just how big could a space habitat get? The focus here is on megastructures designed specifically for living in space, colossal artificial worlds that provide their inhabitants with air, water, farmland, and even gravity. Many of the incredible designs explored today, from O'Neill cylinders to Ringworlds and Dyson shells, already have their own dedicated deep dive episodes covering the engineering details. What this video does is bring them all together, compare their mind-bending scales, and ask just how large humanity's homes in space could ultimately become, what limits their size, and what clever tricks might help us push past those limits. Now, one category gets only a brief mention here, since it received a full dedicated episode recently: zero-gravity habitats, bubble worlds, and smoke rings. Those structures face their own unique scaling challenges, mostly driven by the mass and density of their components. Here, the focus is on habitats that try to replicate something planet-like through spin gravity, massive enclosing shells, or sheer overwhelming bulk. So let's start with the fundamentals. What actually separates a space habitat from a space station, and what laws of physics determine how large we can build them? When we talk about space habitats, there's a critical distinction to make between a station and a true habitat. A station, like the ISS, is essentially a machine, cramped, fragile, and completely dependent on constant resupply from Earth. A habitat, by contrast, is a home. It provides air, water, farmland, and gravity, not just bare survival, but the genuine comforts and scale of civilization. A habitat doesn't necessarily need to be enormous or stationary. Nothing in space truly is, but most long-duration interplanetary ships, and certainly interstellar vessels, would need proper habitats aboard designed for extended living. While a habitat doesn't need to be a perfectly sealed, fully self-sufficient ecosystem, we generally assume they're either largely self-sufficient or part of a broader network of habitats that together form a complete system, much like how a city and its surrounding farmland depend on each other. A broader definition of habitat could include many interconnected space stations working together, and some fascinating variations on that idea get explored here too. But the core definition stays focused on a single large structure or directly connected sections a person can walk, swim, or fly between, with larger collections referred to as communities, clusters, or space nations. Gravity is the very first challenge standing between a structure and a true habitat in space. Without it, the human body begins to fall apart. Bones weaken, muscles waste away, fluids shift dangerously, and long-term health collapses. Forget about recreating a realistic Earth-like ecosystem without something close to normal gravity. Engineering life around zero-G might produce breathtaking wonders, but it will never feel like home. Planets hand you gravity for free, but rarely in the right place or the right amount. So in space, the solution is rotation. Spin gravity. Spin a cylinder, a ring, or a torus fast enough, and centrifugal force creates a very real sense of down. The larger the radius, the slower the spin needed, and the more natural it feels beneath your feet. How do we know this actually works? Simple. Every time a washing machine spins water out of your clothes, it's doing exactly this, pushing mass outward with artificial gravity. Inside a rotating habitat, down points outward toward the hull and up points toward the center. But first, let's crush a massive misconception about gravity in space. The International Space Station does not escape Earth's gravity. At its altitude, gravity is only a few percent weaker than on the ground. Astronauts float because they're in constant freefall, moving sideways so fast they perpetually fall around the curve of the Earth. That's weightlessness. That's microgravity. Now, what happens if you jump inside a spinning habitat? Do you suddenly float? Absolutely not. The centrifugal force from rotation keeps pressing you firmly outward toward the floor. But is spin gravity truly identical to real gravity? Not exactly. In a rotating environment, the pull grows stronger the farther you move from the center. Double the distance, double the force. Real gravity does the opposite, double the distance, and the pull drops to just 1/4. That means your feet always feel a stronger pull than your head in both environments. But inside a spin habitat, you need a structure at least 10 times taller than a person before that difference stops feeling deeply unsettling. Larger habitats solve this elegantly, spinning more slowly to achieve the same gravitational effect, which also dramatically reduces nausea. Like rotating planets, spin habitats also produce Coriolis effects. Move inward or outward, and you'll find yourself deflected sideways. It's barely noticeable in massive cylinders, but strikingly obvious in smaller, faster spinning structures. When it comes to spin habitats, bigger is absolutely better if the goal is an Earth-like environment. The ideal rotation rate sits at 2 RPM or slower, ideally closer to 1 full rotation per minute or even less. That's slow enough that it won't make you dizzy any more than slowly turning around in your chair would. At 2 RPM, you can generate 1 full Earth gravity at a radius of roughly 224 meters, about 733 feet. That's already an enormous structure. But dropping the spin to just 1 RPM makes the experience dramatically more comfortable. Here's the hard truth: cut the rotation rate in half, and you need 4 times the radius just to maintain the same gravity. That's not a minor adjustment. That's an engineering nightmare. And here's where it gets truly mind-blowing. In theory, the most natural habitat imaginable would be one so enormous it only rotated once per day, just like Earth itself. But there's a twist. As habitats grow larger and spin more slowly, the speed at the rim actually skyrockets. Double the radius, and you double that rim velocity. The kinetic energy needed to get it spinning. That scales with the square of the speed. Twice as wide means 4 times the energy to set it in motion. The good news, space is perfectly frictionless. Once spinning, these structures keep rotating for ages with almost no energy loss. This brings us to 2 legendary designs, the von Braun wheel and its ambitious successor, the Stanford Torus. The von Braun wheel is essentially a space station, just 125 feet in radius, generating only Mars-level gravity, a mere 38% of what we feel on Earth. The Stanford Torus thinks much bigger. Over a mile wide with a radius of 894 meters, precisely the 1 RPM sweet spot for full Earth gravity. That's not an arbitrary number. That's physics making the decision for us. Scale up the living space and costs scale right along with it. Air, water, soil, everything inside scales linearly with surface area. You simply cannot cheat the math. Then there are even grander visions, the modified Bernal sphere and the legendary O'Neill cylinder, stretching 5 miles across, 8 kilometers wide, comparable in size to a typical American county. But why can't we just keep scaling forever? Because physics pushes back hard. All that spinning mass creates tension, like a suspension bridge stretched to the length of the entire habitat circumference. Eventually, the materials begin tearing themselves apart. For rings and cylinders, tensile strength is everything. For domes and shell worlds, it's compression and catastrophic buckling under their own gravity. The O'Neill cylinder was designed around steel, with generous safety margins built in. Modern materials like Kevlar or graphene could push those limits even further. And there are engineering tricks that can circumvent even these boundaries. But that's a story for later. At its core, space grants an extraordinary freedom to build on a scale no planet ever could, but it demands a ruthless reckoning with geometry, mass, and the iron laws of mechanics. When most people picture a space habitat, they don't imagine a cramped metal box. They imagine something breathtaking, a vast cylinder or a gleaming ring, farmland curving up the walls, rivers arcing overhead, sunlight streaming in through giant mirrors. These designs captivate because they don't just sustain life, they scale civilization itself. The O'Neill cylinder, the legendary gateway to space habitation. 2 counter-rotating drums, each roughly 8 kilometers wide and 32 kilometers long. A single O'Neill cylinder could comfortably house around 1 million people. And with denser, more urban configurations, that number could explode to megacity scales. But now scale things up dramatically. Enter the Bishop Ring, the massive evolution of the Stanford Torus, and the mind-bending McKendree cylinder. Forget steel. These colossal structures are built from carbon nanotubes or graphene, with radii stretching over 1,000 kilometers, and lengths to match in the McKendree's case. Structures like these offer millions of square kilometers of livable surface, more than the entire continent of Africa, enough to sustain billions of human lives. Step inside one and the horizon doesn't just gently curve upward. Entire continents hang overhead, glittering upside down in the distance. Though at this scale, the atmosphere grows thick enough to blur your view, replacing the rising horizon with a haunting, hazy red twilight band. Scale up even further, and we reach something almost incomprehensible, the Banks Orbital, immortalized in E&M. Banks's legendary culture novels. With a radius of 1.84 million kilometers, dwarfing even the Moon's orbital distance from Earth, this ring rotates just once per day, delivering perfect natural gravity and genuine 24-hour day-night cycles, with no mirrors or artificial lighting required. Even at a modest width of just 1,000 kilometers, a Banks orbital delivers a staggering 3 billion square kilometers of surface area, 6 times the entire surface of Earth. Widen it to 10,000 kilometers, and suddenly you have the equivalent of 60 Earths worth of land. The design can't be made arbitrarily wide or cylindrical, though. Natural sunlight from a real star is the entire point, and proportions matter. Push too wide relative to the radius, and you block that precious light. The practical maximum reaches perhaps 200,000 to 300,000 kilometers wide, translating to 1,200 to 1,800 times Earth's total living area. And if you need even more space, simply build more of them, orbiting the same star. You can even chain them together, though creating a seamless, walkable connection between them becomes an extraordinary engineering challenge. Now, no known material could survive the crushing strain these structures demand. But there is a workaround, and we'll get to that shortly. First, let's push the boundaries even further. The Ringworld. The Ringworld is the ultimate dream of megastructure engineering. A ribbon the size of Earth's entire orbit, 300 million kilometers in radius, with a habitable inner surface offering more land than 1 million Earths combined. Stand on it and the horizon curves not gently upward, but forever. The sky is framed by mountain-sized walls containing the atmosphere, while rivers and continents sprawl for light minutes around the central star. It's a breathtaking, almost sacred vision, born from the brilliant mind of the legendary Larry Niven. And yet it's a concept that critics have long dismissed as utterly impossible. The usual objection is material strength. To spin at 1g rotational speeds, the rim must endure tangential velocities of over 1,000 kilometers per second and exert stress on structural materials that no known substance could survive, though the hypothetical material known as mag matter could. By conventional thinking, those stresses would tear it apart long before construction finished, and it would be spinning fast enough that its debris would actually reach interstellar escape velocity. But this problem is not insurmountable. The trick is to decouple the habitable band from the need to carry all that load itself. You don't build the Ringworld or the Banks Orbital out of one miraculous unbreakable material. Instead, you nest this ring inside a far more massive and slowly rotating outer ring. The inner and outer rings combined would have a net angular momentum equal to what all that mass would normally need to orbit the star, circumventing one of its core support problems. But more importantly, they push back against each other. The inner ring presses down hard on the outer ring below it. When they are not touching and are separated by vacuum, magnetic forces keep them apart and distribute the load across both structures. This outer ring can be filled with cheap, abundant mass like hydrogen and helium, and it also serves as a protective shield for the inner ring. It's worth noting that all of this is orders of magnitude easier with the Banks orbital, which also avoids the need for sun squares between the inner ring and the star to block light half the time for nighttime, or twilight bands for that matter. One remarkable feature of the Ringworld concept is that you can actually create a habitable Dyson sphere this way, by stacking mini rings, each slightly wider or narrower than the last, so they never quite touch, tilting each at an angle until the entire star is englobed. Travel between these rings as a single habitat is tricky but achievable, and the result offers 2 billion times the total living area of Earth when built around our Sun. That figure tends to be the upper limit for most megastructural configurations, since you need power to run life support, and our Sun outputs roughly 2 billion times the energy Earth requires to sustain life. Though that isn't a hard ceiling, and there are ways around it. So while many will say a ring world is impossible, that's more a reflection of how daunting the scale is than any final verdict. With clever engineering and enough raw material to forge entire planets into girders and stabilizers, it becomes less a fantasy and more an extraordinary challenge. A Ringworld Dyson sphere would not be easy, but it remains a vision that fits within the laws of physics, provided we accept the structure is not a single ribbon, but a whole ecosystem of rings. That said, the Banks orbital is likely as large as anyone would realistically go, simply because it already pushes into the BWC megastructure range, where an equivalent amount of living space can be achieved far more cheaply across many smaller habitats. A BWC megastructure, incidentally, stands for because we can, and these structures exist mostly to prove that you could build them if you wanted to, rather than for any truly practical reason. A cube-shaped planet, for instance, is entirely doable, but mostly just weird, except as a novelty. A giant disk world, or flat Earth, is actually a borderline viable concept, one that holds some surprising practical advantages over traditional worlds and could even fit certain niche applications. But today, we're exploring how humanity might engineer immense structures in space. And what if we could also engineer time itself? In an exclusive deep dive episode, Chrono-Engineering, Manipulating Time as Technology, we examine every option under known physics and push into the wild frontiers of cosmology and science fiction. From the very real-time dilation we already correct for in systems like GPS, all the way to wormholes causality engineering, and what a civilization looks like when time becomes something you actually allocate. Now, let's talk about the Topopolis. Practicality in construction is always a real concern, but habitats don't have to scale in just one direction. A cylinder is really just a ring stretched along its axis, and making a cylinder longer adds no structural stress the way making it wider does. That brings us to the Topopolis, another brilliant invention of Larry Niven, which keeps the same radius as a standard spin gravity habitat, but can be made almost arbitrarily long. Imagine a tube only as wide as an O'Neill cylinder, about 8 kilometers or 5 miles across, but stretched out as far as you could possibly want. A Topopolis around 20 million kilometers long would match the total living area of Earth. Stretch it to 20 billion kilometers, and you have roughly 1,000 Earths worth of space. Push it to 20 trillion kilometers, and you're looking at 1 million Earths, though by that point, your Topopolis stretches over 2 light years, reaching from one star toward the next. Here's the fascinating part. Every material, no matter how rigid, eventually bends and knots like yarn if made long enough. Even spinning doesn't prevent that. So the Topopolis practically invites you to loop it around things. You could create one giant ring around Earth or Jupiter, weave multiple loops together, or even form a tangled ball encircling an entire star, billions of kilometers of habitat in total. It's also worth noting that a rotating habitat has absolutely no reason to be exposed directly to space. Unless windows for sunlight are desired, the entire structure can be sheathed inside a slightly wider, non-rotating outer sleeve. That outer layer could be packed with cheap hydrogen or helium for radiation shielding, or carved directly into an asteroid by boring a cylindrical tunnel straight through it. In a Topopolis, this approach allows multiple rotating tubes to sit side by side like threads bundled together with transport systems linking them. Instead of one endless corridor, you get a braided network of interconnected habitats. And since they rotate slowly enough, connecting them to the non-rotating outer sheath becomes surprisingly manageable. A home inside one could even have a transport tube running through its basement, giving direct access to the sheath layer. And there's no reason to stop at O'Neill-sized tubes. If your materials allow it, you can always scale up. Carbon is far more abundant than iron, so if you can mass produce it, why bother with steel when you could build with graphene instead? A graphene Topopolis with a 1,000-kilometer radius would need only about 80,000 kilometers of length to match Earth's entire surface area. Scale that up to a Dyson-level megastructure, and you're looking at 100 trillion miles of ribbon wrapped around a living star. That's roughly 17 light years, long enough to physically connect entire star systems. And why stop there? Using stellar thrusters, you could bring two stars to a relative halt and string a Topopolis directly between them, weaving a cosmic web of ribbon that engulfs both suns in a breathtaking celestial tapestry. You could literally walk, swim, or fly between a pair of stars. Topopolises have so many mind-bending possibilities they deserve their own dedicated episode. But at their core, life inside one would feel like an endless river valley, cities and farms strung like pearls along a highway that stretches forever into the horizon. You could spend your entire life walking downstream and never reach an edge, because there isn't one. Eventually, the structure loops back on itself anyway. From the outside, it might look like a tangled cosmic ribbon, orbiting planets or threading between stars. And the most stunning part, none of this requires magic. Even redirecting stars using modified star-lifting engines is just mirrors and magnets scaled up to jaw-dropping proportions. It's epic engineering, but technologically simpler than a wristwatch. Now that we've explored rotating habitats, let's look at something completely different. Not every habitat has to drift freely through space. Sometimes the boldest move is to take a world and simply wrap it. Perhaps the most straightforward option is building a massive greenhouse directly on a barren planet. The most modest version covers smaller regions with transparent domes, sealing cities, craters, or valleys under gleaming roofs, creating a patchwork of livable zones on otherwise deadly worlds. This doesn't create new land, but it dramatically multiplies usable area on marginal planets and moons. And it scales beautifully from a handful of domes for a small colony to thousands blanketing an entire world. Push that concept further and you get the world house, a colossal greenhouse stretched across an entire planet. The roof could be a thin but incredibly strong film suspended kilometers above the surface, held up by towers, cables, or even atmospheric pressure itself. Beneath it, the climate could be dialed in to perfect Earth-like conditions. A world house could make Mars livable without waiting centuries for full terraforming. The real challenge isn't structural, it's heat. A world house traps sunlight devastatingly well. Without shading systems and radiators, it rapidly becomes a planet-sized oven. But that also means it works brilliantly on worlds far outside the traditional habitable zone. These structures don't have to be planetary in scale either. You could englobe an asteroid or a moon the same way, delivering atmosphere and climate control even in low-gravity environments. One wild option for boosting surface gravity is embedding a small artificial black hole at the center, assuming you don't already have Star Trek-style artificial gravity on hand. Natural gravity drops off at the inverse square of distance. Deep inside a tiny asteroid just 10 kilometers wide, a hidden black hole could generate Earth-like gravity at the surface. But climb just 10 kilometers higher, and that gravity plummets to a quarter of normal. Here's the shocking part. Surface gravity alone doesn't hold an atmosphere in place. What really matters is escape velocity, which depends on total mass. For a world this small, that escape velocity would be a mere 443 meters per second, barely faster than the speed of sound, and just 1/20th of Earth's. Without a sealed roof enclosing the habitat, the atmosphere would bleed away into space. And if that roof ever cracked, the air would explode outward at deadly lethal speeds. A habitat like this would require a mass of roughly 1.5 times 10 to the 19th kilograms, about 1/1400th of Earth's total mass. Interestingly, the surface area would scale by that exact same fraction, so the math works out beautifully. To achieve normal gravity on a normal matter world, mass must scale in direct proportion to surface area. But cramming that much mass into something asteroid-sized demands extraordinarily dense material, and that's precisely where black holes become invaluable. Now let's think even bigger. Sometimes building a better world means making it less dense, not more. Saturn, for example, has nearly the same surface gravity as Earth, yet packs roughly 100 times the mass and surface area. Earth is the densest planet in our solar system. Saturn is the least dense. Yet standing on both would feel surprisingly similar if Saturn actually had a surface to stand on. Encase a Saturn-like world in a rigid shell, slow its spin to a 24-hour day, and nudge it closer to its star, and suddenly you have a habitable world 100 times larger than Earth. And there's no real ceiling on ambition here. Wrap a shell around a massive black hole, and you could engineer a world with Earth-level gravity, but 1,000,000 times the living space, rivaling a full-scale Ringworld in sheer scope. Unlike a Ringworld, though, such a shell can't orbit a star to create natural day and night cycles. Instead, it would require artificial lighting, and ironically, black holes are perfectly suited to supply that power, drawing from the enormous energy of accretion disks and intense magnetic fields. The true brilliance, however, lies in stacking. Each additional shell layer adds only a modest amount of mass, yet creates an entirely new world that inherits gravity from everything below. Since artificial lighting is already necessary, the floor of one level simply becomes the ceiling and light source for the level beneath it. At the most breathtaking scale of ambition, we arrive at what are called Matrioshka Shellworlds, towering stacks of artificial habitats, each possessing its own sky, land, oceans, and atmosphere. Massive support structures, known as Atlas pillars, hold each layer apart, threaded with elevators and tunnels connecting the levels. A single converted planet could host dozens of these layers, each as vast as an entire continent. Done right, Earth itself could be transformed into a megastructure supporting trillions of inhabitants across its stacked surfaces. The critical limitation is heat. Every new shell traps warmth from the layer beneath, making thermal management and energy balance increasingly complex as the stack grows. The most extreme version of this concept is the Birch planet, built not around a stellar mass black hole, but around the supermassive giants lurking at galactic cores, containing millions or even billions of solar masses, pushing the boundaries of what's physically conceivable. Planetary rapid habitats like these offer the rock-solid stability of natural surfaces combined with the limitless freedom of deliberate engineering. They're not as free-floating or modular as cylinders, but they transform the worlds we already have into breathtaking, multi-layered jewels of civilization. Alternative and exotic designs. Beyond cylinders and domes, there's a whole universe of strange and spectacular ideas waiting to be explored, some brilliantly practical, others pure mind-bending thought experiments, but all of them reveal just how incredibly flexible space habitats can truly be. Asteroid colonies. The most obvious path. Hollow out an asteroid. Carve out the interior, reinforce the walls, and insert a rotating habitat inside. The rock itself acts as natural radiation shielding, and as you mine it out, you just keep drilling deeper. These internal habitats can connect to a Topopolis or link through pressurized corridors, even thinner rotating tunnel habitats threading between them. You could pack thousands of habitats into a single asteroid, expanding the livable space over time as mining hollows it further. Individually modest, but with millions of asteroids in the belt, the cumulative living space could dwarf Earth many times over. Bucky habs. Multiple rotating habitats can be linked together in fascinating ways. The sausage link approach is the easiest to picture, but you can also form a geodesic lattice, a Bucky hab. The connection points become pressurized spheres, with cylinders narrowing toward their end caps, dropping gravity as they taper into microgravity junction zones. These lattices come in countless varieties, flat hexagonal grids, fully three-dimensional arrangements, and mixed configurations where not every habitat shares the same dimensions. Rungworlds. Then there's the rung world, and that's rung like a ladder, not ring like a ring world. A rung world takes rotating cylinder habitats and arranges them like rungs on a cosmic ladder. The long arms could be a Topopolis, a pressurized microgravity corridor, or an unpressurized transport spine, or all three combined. Imagine that ladder bent into a circle, wrapping around a planet or even an entire star. Unlike a ring world, a rung world requires no impossible tensile strength. It's completely feasible with conventional materials, given enough of them. Like a ring world, you can tilt and stack multiple rung world structures at different angles until they form a dense sphere around a star, a true Dyson-like swarm. Each rung is simply a rotating habitat of arbitrary size, with its radius constrained by the same material limits as any O'Neill or McKendree cylinder. A rung world at geostationary altitude around Earth could circle the planet with its rungs, while the gaps between them fill with solar collectors. Over time, more rungs and habitats get added wherever needed, gradually completing an entire belt of civilization. Rung worlds can scale without limit. Their radius could reach truly astronomical proportions, Kardashev Type 3 levels of power and scale. Imagine a rung world framework built not around a planet or a star, but around an entire artificial dwarf galaxy, each rung a world unto itself, strung together into a cosmic ladder of civilizations. Flat Earths and Alderson disks. Flat Earths have been explored before, not quite in the same league as the greatest megastructures ever conceived, but still absolutely mind-blowing. There's an entire concept dedicated to the challenges and possibilities of actually constructing one. While evenly distributing gravity across a disk is tricky, it can absolutely be done. The main reason to build such a world. A coin-shaped planet can generate its own day and night cycles simply by spinning, and it would have identical seasons everywhere across its surface. That means you could engineer an enormous resort world without wasting a single gram of mass on unwanted polar regions. There are limits on how large you can build one if you rely on rotation for lighting, but if you're willing to illuminate it with artificial sources, there is no fundamental size cap whatsoever. At the farthest extreme of that concept lies the Alderson disk, a vast plate wrapped around an entire star, extending billions of kilometers in radius. Its mass would exceed that of every planet in the solar system combined, and it would require active structural support just to keep from collapsing under its own staggering weight. It's also a wildly inefficient way to capture starlight. A Dyson swarm would do that job far better, but the Alderson disk represents one of the largest continuous surfaces ever imagined by human minds. While it's not a practical design, there are ways to make it viable. It illustrates a breathtaking principle. There is no clear upper limit on how enormous a habitat can grow, short of full-scale stellar engineering. These alternative visions remind us that a habitat can mean almost anything, from hollow rocks to geodesic networks to world-spanning plates. These limits are set less by physics than by the boundaries of imagination itself. So the boundaries of possible habitat sizes have been pushed to the extreme, but would these colossal structures actually get built? The honest answer is that most habitats constructed will likely be smaller. And not just in sheer quantity, the majority of total living area will exist inside these much smaller structures too. Just as there are far more houses than skyscrapers, yet vastly more total living space inside those houses than inside the towering few. And yet, because we can, megastructure is almost certainly going to be built anyway, because civilizations love a challenge. In a Dyson swarm of a quadrillion O'Neill cylinders in smaller habitats, a few flat Earths represent a fairly trivial expenditure, a spectacular place to store helium for future use, and a tourist destination people will absolutely want to visit. Now scale that up from the immensity of Dyson swarms around our own sun to billions of other stars, each with their own eventual Dyson swarms, and it becomes overwhelmingly believable that megastructures of epic scale will be built, even when not entirely practical. Imagine a galaxy where less than a trillionth of all living area was cube-shaped planets, And yet, in a Kardashev Type 3 galactic civilization, that would still mean a billion Earth equivalents worth of cube worlds just hanging there in space. The same goes for donut planets, flat Earths, and stranger things still. But what's truly astonishing is that scaling up is often not impractical at all. Rogue worlds, buckyhabs, and Topopoli require no extraordinary feats of engineering. They may be just as straightforward to build as conventional habitats with obvious and powerful appeal. So just how big can a space habitat get? The answer stretches from a simple dome over a crater all the way to a ribbon looping endlessly between the stars. Every leap in scale brings breathtaking new challenges and mind-blowing new wonders. What's absolutely clear is that we are not prisoners of the planets nature handed us. We can build our own as massive, as bizarre, and as numerous as we dare to dream.